So in section 3.1.4, Laplace's equation is actually finally used in 3 dimensions. So let's go back and copy Laplace's equation that we had. So it's going to be this one here. And finally, we have it in 3 dimensions. So it's going to be very easy. Now, one thing that I actually think that it's a great way of explaining it is imagining a bubble you made with soap and water. When you have this bubble, you have a perfectly rounded sphere. There's no such thing as a valley over here. There's no such thing as another bubble coming out like this, as long as it's, of course, a bubble not affected by anything on the outside. Because we're imagining that on the outside, the potential, the charge is equal to 0. So in real life, it would be that there's no wind and no other sources. Therefore, we have a perfectly shaped bubble, a perfectly shaped sphere. And of course, we know that the average value of the potential of a sphere will be the same as this equation over here. So it will be 1 over the surface area of the sphere, which is 4 pi r squared, and then the integral of this sphere of the potential times the of the area. Because of course the area, because we're talking about 4 pi r squared, which is the area. So now, as you can see, the bubble, there's no local maximum or minimum. Like I just said, there's no such thing as a value over here and something like this. This is not a bubble. A normal bubble would not exist like this. Or there's no such thing as another blob coming out of it like this. There's no such thing as this. So everything is perfectly shaped. And therefore, when you have the potential on one point over here and the point over here, the average value will be the same as the potential over here. If we imagine for a bubble, we imagine that, for example, the average position of this bubble is going to be the position at the center. Or if we imagine, for example, another ball, we can, for example, imagine that we have a basketball. So let me draw a little other sphere. A basketball with all those signs. And you see those players rotate the basketball on their finger. You know that they put their finger on the bottom right here. So here they'll be their finger. That's because the center of mass will be right here. Because the average of all the masses from all the points around, so between these 2 points, the center will be right here, the average will be right here, the points right here and right here, the average will be right here, when all combined, will be right in the center. And so if we put the center right on top of our mass, our finger, it means that the whole ball will stay in equilibrium. So if we were to rotate the ball, for example, and put our finger on this side, let me put it. Okay. Our finger on this side, and the gravity was actually pushing on this side, it means that our force center gravitation was still on the same point. Therefore, it's always going to be in equilibrium on our finger right here. As you can see, then there is also a very good example that explains exactly what happens with a 3D sphere and the potential given by an external point. But as you can see, it's going to tell you simply that the average potential given by a charge Q given by the whole surface is going to be simply the same as the charge on the inside. I actually made a video about this, solving the example, and I will put the link in the description of this video if you want to go and see it.